Okay, guys. So far in our study of operational amplifier circuits, we've taken a look at three separate circuits. We had the inverting amplifier circuit. We had the summing amplifier circuit. We also had the non-inverting amplifier circuit. I'm sure that you can guess just based on the names that there is a difference amplifier circuit. This one, in terms of the analysis, is the most difficult, the most subtle. This is one of the reasons why we left it towards the very end. But let's go ahead and start taking a look at it. Remember that the assumptions that we had made in the previous analyses and even the method of analysis is it's going to stay consistent. It's going to stay very, very, very similar. However, I am going to perform a few feats of mathematical acrobatics. So just be aware that we are going to have to do some bookkeeping here. And I already know the tricks. I want to show them to you, right? So if you're questioning why am I doing certain things, keep in mind that it will become clear by the end of the analysis why I kept things in a certain way, right? So let's begin with the title of this. So this is the analysis of the difference amplifier circuit. Let's see. I do engineering, not spelling. I can't spell circuit. There we are. Okay. Now, again, the goal is to find the output voltage as a function of the input voltages and the rest of the components. So this circuit looks like the following, the circuit schematic. We have our operational amplifier with our non-inverting and our inverting terminal. We're going to hook this up to plus and minus VCC. Now, one thing that I also wanted to make mention of in terms of hooking this up to plus and minus VCC, notice that I consistently, every time I draw my circuit schematic, I put in plus and minus VCC. One of the reasons I do this also has to do with how you put these circuits together experimentally. I would say that 75% of the time in the laboratory, when students cannot get their operational amplifier circuits to work, it's because they neglected to hook these up. So once you have placed your amplifier onto the breadboard, you should always include immediately before you start hooking up the rest of the circuit, you should also include plus and minus VCC. This is one of the reasons why I do it this way. Now we do have our voltage output on this end, not, and now at the non-inverting input, we have one resistor down here, followed by ground. We have one resistor right there, followed by a voltage source, like this. At the inverting input, we have our feedback resistor, negative feedback, not positive feedback. We have one other resistor there, and then we have a second voltage input right here. Now, in terms of the names of these voltage inputs and resistors, this is VA, this is VB, this is RA. Right here we have RB as the negative feedback resistor. Here we have RC, and lastly we have RB. Right. Now, let's state a few things. The first is our assumption. I'm sure that by now you've hopefully memorized this. So here we're going to assume that this is an ideal op-amp, which means we have two input constraints. The input voltage constraint is that V sub P and V sub N are same. Oops, that's not 2 and 3, that's 1 and 2. And the input current constraint is that the currents going into those terminals of the op amp are 0. Now let's go back and take a look at all of the nodes. So there is one node here. There is also a node there. There's one node right there. There's one node right there. And then lastly, there's one node right there. So this has a few nodes. Let's now take a look at a few variables and define a few variables. So here we have our node P. This is at a node voltage V sub P. And we in general have a current I sub P flowing into that terminal. Here we have our node N. This is at a node voltage V sub N. And in general, we're actually going to have current I sub N flowing in like that. This is at a node voltage V sub naught. This is at a node voltage V sub B, and this is at a node voltage V sub A. So we have all our node voltages of interest already labeled. Now, unlike the previous analyses where we wrote down KCL at node N, we took a look only at node P, and we were able to achieve our goal of finding the output voltage. This one's trickier, right? This one's longer, right? So I'm going to begin by taking a look at node N first and writing down an equation using KCL for it, and then I'm going to use KCL with node P. And one of the things that you're going to see is things are not as simple as they were in the previous analyses. Right? So again, we're going to have to bookkeep. So we're going to use the node voltage method. And I am going to begin by using KCL at node N. And the version of KCL is that the sum of the currents flowing out of this node adds up to 0. Like this. Now, at this node, there are a few currents flowing out of it. We have a current flowing from there to there, current flowing from there to there, and then a current flowing from there to there. So here we actually have the sum of 3 currents. Let's go ahead and write them down. So here we have current going from V sub N to V sub A to R sub A. So we have V sub N minus V sub A over R sub A. We also have the feedback current going from V sub M to our output voltage divided by R sub B, and then we have plus I sub N, and that's equal to 0. This is going to be my equation 3. Now let's go ahead and simplify this as much as possible. We can use equation 2, the input current constraint, just immediately to say that that current is 0, right? And what I'm going to do is I'm going to solve for our output voltage. That's what we want anyway. We want our output voltage by itself. So from 3, we're going to solve. Let's do that in black. I want to solve for V naught from 3. And the easiest way to do it, I don't know about you guys, I don't like fractions within fractions. So I'm going to go ahead and multiply by RB, get V naught essentially on its own. So I'm going to take this, multiply everything by B. So if I do the multiplication, I get RB times V sub N over RA for my first term. So that is this times that. I also have to multiply that by that. So I have minus RB times V sub A over RA, and you'll see why I split it up here in a second. Then I need to distribute to the next term, and that RB cancels out very, very cleanly. Cancels out very cleanly with this one. So these two essentially cancel out. However, I do still have the sum of those terms, so I have plus V sub N minus V naught is equal to 0. Now I can very easily solve for V naught So here I'm going to add this term to the opposite side. And what I'm going to do is I'm going to group this term and that term together because they have a v sub n. So here I have v naught is equal to 1 plus rb over ra times v sub n. And then I still have minus rb over ra times v sub a. And I'm going to call this equation 4. So hopefully you can convince yourself that this whole thing right here is identical to the equation above. If it's not absolutely clear, then I go back. I would go back and make sure that you see that they are the same thing. Right now, it's ugly. Granted, it is ugly. Right? But the advantage here is that v sub n only appears there. So that's where you're going to see that this becomes an advantage. Now, this is as far as we can get by using KCL at node n. Let's actually now use KCL at node p. So let's use KCL at node p. And the version that we're going to use is the sum of the currents flowing out of this node and to zero. So let's go back up to our node p and figure out what currents we have there. We have current flowing from node p to that node, so that voltage source. We have one flowing into the op amp right there, and then we have one flowing there. So once again, we have the sum of 3 terms. Right? Let's write down what those terms are. So we have Vp minus Vb divided by, in this case, we have to be careful. That's flowing through the resistor RC. Like this. We then have going down the ground. We have that current. And it's flowing through RD. So we have a current flowing from there to there. And that's going to be V sub p minus 0 over RD. So V sub p minus 0 over RD. Right? And then plus I sub p, and that has to add up to 0. So right here, those are the 3 terms. We already got to equation 4. I'm going to call this equation 5. But we can once again simplify this by using the input current constraint. So the input current constraint tells us that current is 0. Now what I'm going to do, and it's not obvious why I should do this, is I want to solve for Vp. The reason I want to solve for Vp is because I know V sub n and V sub p are the same thing. Right? So over here, the way I'm going to solve for it is in the following manner. I'm going to multiply everything through by r sub d. Right? If I do that, then I have r sub d over r sub c times Vp minus r sub d divided by r sub c times Vb. And then I have plus V sub t, and that's equal to 0. Right? I can add this term to the opposite side, and then I'm going to group this one and that one and just factor out V sub p. So here, if I factor out V sub p from those 2 terms, I'm left with 1 plus Rd or Rc times V sub p, and on this side I have R sub d divided by R sub c times Vb. So here I'm solving for Vp. And solve for VP, we can divide both sides by this. So here, V sub P is equal to RD over RC is V sub B, 1 plus RD over RC, and I'll call this equation 5. That's 6. I know, it's gross. I didn't invent how this operational amplifier works, but if we want to study how it actually does function, sometimes we do have to go through the mathematical mess and really bookkeep things. Um, but the nice thing about what we have so far is since we solve for V sub P, we have the second of the op-amp assumptions that V sub N and V sub P are the same thing. So I can conclude here, since by equation 2, V sub P is equal to V sub N, right? And V sub N, V sub P was shown to be this RD over RC times VB divided by 1 plus RD over RC. So this equation 7, I can use 7 in the other one that we obtained from KCL in equation 4, right? And plug it in right there, right? So let's go ahead and do that. Let's actually do the plugging in. And we have to be careful with our terms. So we have 1 plus RB over RA times V sub N. So we have the output voltage, which is 1 plus RB RA times V sub N. V sub N is that nastiness. So we have R sub D divided by R sub C times VB. And in the denominator, we have 1 plus RD over RC. And we can't forget the term. We have minus RB over RA times V sub A. Call this equation 8. And you can see why this one was left at the end. This is what she wrote. This is what we were actually after, right? Now, notice that the relationship between the output voltage, the input voltages, as well as the rest of the resistors, it's a complicated relationship. It is not a simple relationship, right? But as always, I want to make one observation, right? I'm going to take a look at a special case. So let's take a look at the observation. And the observation for the special case is if we choose our resistors such that RB divided by RA is equal to RD divided by RC, then the following thing happens. So I'm going to use this in equation 8. And in particular, anytime I see RD divided by RC, I'm going to replace it with RB over RA. And notice that that occurs right there and right there. Two places where it occurs. So here I can rewrite V naught is equal to 1 plus RB over RA times RB over RA. That's the replacement times VB. And the denominator, I have 1 plus, there's another replacement, RB over RA. And then I have minus RB over RA times VA. Look at what happens here. Notice that this and that cancel out perfectly. On top of that, we have this term and that term in common, in which case we get V naught is equal to RB divided by RA, and very easily VB minus VA. This is what I want to look at. This is where the operational amplifier gets its name. This is called the difference amplifier circuit. And notice that when everything essentially falls out, the final expression, you have the input voltage VB minus the input voltage VA. So this is again one of the reasons why we call this the difference amplifier circuit. And thank you for watching.